Hello everyone, and welcome to this video on section 4.3 called Separable Equations. In this video, I'm going to be taking you through a preview version of a Knewton Alta assignment for this section 4.3 on separable equations. Please understand that the questions I see in this video may not be the same exact questions that you see when you work on the assignment yourself. But the objectives are the same. Hopefully the problems are similar enough that watching me work through them will help you in some way when you work on them on your own. Okay, so here's our preview Knewton Alta assignment. Got the title in the upper left-hand corner, got your mastery bar in the upper right-hand corner telling you how far along you've gotten, the activity log showing you how far you've gotten in each objective, and I have it toggled on to where you can switch between the bold heading objectives, not the individual ones, but I could start this section finding particular solutions and solving applications using separation of variables. I could start that anytime I wanted, but I'm not going to do that. Then you have a current objective, and underneath it, a question related to that objective. And at the bottom of every question, you should be seeing a feedback button. So if you're seeing any errors in the question, typographical errors or errors in the answer explanations, you can send feedback directly to Knewton, and hopefully someone will respond to you quickly and fix the problem. You will not have this instructor cheat button. This is for instructors only. You will have a more instruction button. All right, so if there's ever a topic you're having an issue with or struggling with, try clicking on this. It'll take you to a page with some reading to do or videos to watch or both. And then you'll be given a question, related to that extra instruction. And you can work through the assignment that way, through the entire assignment. Click on this more instruction button every single time if you wish. Okay. So the first objective I'm seeing here is use the separation of variables technique to find constant solutions and set up integrals to solve differential equations. All right. So the first question, find any values of y corresponding to constant solutions for the differential equation y prime, the first derivative of y, equals the natural log of 5y multiplied by the cosine of 2 pi x. And then we're asked to separate multiple answers with a comma and enter your answers in a simplified exact form. And if there are no real solutions, enter the empty set symbol or this, circle with a slash through it. So we are simply asked to find constant solutions here. So let me write this out on some paper and go into what that means. All right, so my equation, the differential equation we're given here is, y prime or dy over dx, it's the first derivative of y with respect to x, is the natural log of 5y multiplied by the cosine of 2 pi x. Right, so this equation is what they would call separable. because it is of this form. You have y prime equals, and this is y is the dependent variable and x is the independent variable, is equal to some function of the independent variable multiplied by some function of the dependent variable. Okay, so any equation, first order equation, that can be expressed this way would be called separable. So you see here I've got y prime equals, and then here is this function of the independent variable, right, f of x, this cosine of 2 pi x, multiplied by, and then the function of the dependent variable, right, the natural log of 5y, I'll call this, g of y. So I recognize this as separable. Now, they're not asking me to find the general solution to this. They're only asking me to find any constant solutions. All right, so I'm being asked to find a constant or any constant solutions to the differential equation. So that means y equals, some constant. I'll put capital C to represent a constant. We're just looking for values of C that will make this work. Well, if y is a constant, then y prime, right, dy over dx would just be 0. And throwing these into the equation, we'd have 0 on the left equals the natural log of 5c, right, y is constant, y equals c, times the cosine of 2 pi x. And again, I'm just looking for values of this c that would make this true. So over on the right side here, I've got a product equal to 0. And you may recall by the zero product property, right? If you have a product equal to 0, then either factor could be 0, and it would still be true, right? So this natural log factor could be 0, or, this cosine of 2 pi x could be 0 as well. But, we're not going to get any information out of this. I mean, yes, this has solutions. There are values of x that would make this work. But we're not looking for x. We're trying to find these constant functions. Y is a constant function here that makes this work. So there's no y in this, no c. So, I'm not worrying about this equation. Even though there are solutions, there are values of x that would make this work. Like I said, we're only looking for these, right? These y equals some constant. So the only equation that's going to give me information out of that is this. This equation here has the c involved. And if I solve for c, that would mean that 5c must be equal to 1, right? E to the 0 power. And so the only value of c that would actually work here is 1/5. So y equals 1/5. This is a solution. Again, I say a solution of this differential equation, and I'll abbreviate differential equations with DE. Now that is, again, that's a solution. It's a constant solution. Now, if they asked me to find the general solution to a separable equation, we'd have to go about it a totally different way. Actually separate the variables, separate the y's from the x's, and then integrate. but we are not asked to do that here, right? We're only asked to find these constant solutions, and the only one we found was y equals 1/5. Okay, so back in the assignment, y equals 1/5, and there aren't any more, so I don't need to do any commas. I said if there are multiple answers, we'll separate them with a comma. I didn't find multiple answers. Right. And submit. Great. And after every problem, every question, if you get something wrong, they may ask you to try again one more time. And if you get it wrong again, then they'll tell you it's wrong and give you some sort of answer explanation. But even if you're right, they'll give you an answer explanation. Either way, I would recommend looking through these answer explanations, just to make sure you understand what's happening, right? If you got it right, maybe the answer explanation will have some sort of information that you like better. They did it in a different way that you like better, that you might try for future problems. Now, if you got it wrong, definitely read through the answer explanations and try to figure out where you went wrong. And hopefully that'll help you with future questions like that. All right, so let's continue on. All right, so they have skipped to another objective. I'm seeing find general solutions to differential equations using separation of variables. All right, so this is what I was talking about in the last example. They're not asking me to find constant solutions, but, the general solution to a differential equation. So I'll write out this equation here, and then we're going to see how it's separable by factoring the right side. We're going to factor the expression on the right side here so that it is a function of x multiplied by a function of y. And now you'll see this separation. So here's our equation at y prime. Now I'm going to write it this way, right? dy over dx with differentials, right? That's y prime, first derivative, equals, and then the expression on the right side, got this polynomial in x and y, is 3x squared y plus 9x squared plus 2y plus 6. Now this is not of the form f of x times g of y, right? Again, remember what I said on the last example, right? An equation is separable if it can be expressed this way. Y prime equals, some function of the independent variable times some function of the dependent variable. And when they talk about solving an equation like this, here's what's going to happen. You have dy over dx over here. If I write the derivative in differential form, equals, some function of x times some function of y. I'm going to separate the variables, gather all the stuff with y on one side, right? So that would require dividing by g of y, and all the stuff with x on the other side by multiplying by this differential of x. And remember, you can really only manipulate differentials this way when it's a first order differential. So, treat it like a fraction, kind of, multiply by dx. So then we have f of x times dx. And then you integrate, then solve for y if possible. Okay, it might not be practical or easy to solve for y, I'll say solve for y if possible. Yeah, you may not be able to solve for y in certain cases, so then you would just leave it the way it is, and it will be implied that y is some explicit function of x, but they are asking us here to give a y equals, find an explicit solution. Okay, so back to the example. This polynomial on the right side here is not a function of x times a function of y separated like this, but I can factor this by grouping. The first two terms have 3x squared in common, and if I remove 3x squared, pardon me, from the first two terms you'll have y plus 3, and then the second two terms, plus, and then these have a 2 in common, also times y plus 3. And now look at the thing as a whole. Both of these products have the quantity y plus 3 in common. All right, so now I can see that this is a separable equation. You got y plus 3 multiplied by 3x squared plus 2. So here's their function of x times function of y, right? F of x is like this 3x squared plus 2 here. And the g of y is y plus 3. So now I see, it's separable. I'm going to go about solving it the way I described over here, finding a function y of x that will satisfy this. So I do the separation. I get the y plus 3 over on the left with the dy. So we have dy over y plus 3. And then the dx over on the other side with all the x stuff with the f of x. All right, so 3x squared plus 2 dx. Now that I have the variables separated, we integrate, integrate with respect to y on the left side and integrate with respect to x on the right side. Now on the left side, that's simply the natural log of the absolute value of y plus 3. Now I could put plus some constant here, but you're going to see that, I'll say this out loud. If I put plus constant on the left and plus a constant on the right, you could just subtract one of the constants and get a simple constant on one of the sides, say on the right side. So you don't need to put plus constant on both of these, right? Just one of them will suffice. So I typically like doing it on the right side with all the x stuff. All right, so we have the natural log of the absolute value of y plus 3 equals, and then when I'm integrating the right side with respect to x here, the x cubed plus 2x, and like I said, plus some constant, right? So we can see for some constant. And now this right here, this is not my final answer, but this right here does describe the solutions to this differential equation. But how y is not solved for, right? Y is not alone. But it is implied that y is a function of x here. So they would say that this particular, what I have in the box here, describes the solutions, the functions of y, the functions y of x, implicitly. Right? So they would say that this is this is the implicit solution or implicit form of the solutions of this differential equation. But they want us to solve for y. They want, what is y explicitly as a function of x. So now I need to get y alone. So exponentiating both sides here, right? making both sides a power on e, base e, you'd have y plus 3 on the left equals, e to this x cubed plus 2x plus some constant, power. Now, a way you might see this written, another way you might see this written, I mean, this is totally fine right here, is when you see sums and powers, you can rewrite this as a product. This could also be written as e to the x cubed plus 2x power, with the variable stuff, multiplied by e to the constant. But this e to the c, this is also a constant, right? It's a constant raised to another constant. This is a fixed value. There are no variables in this. So because it's also a constant, very often you'll see them do this. Hey, I have another constant here. I'm going to call it C again. Keep calling my constant C. Now be careful. All right, be careful. I'm going to replace this e to the c with c, but the c is not the same c as the first one. All right, so you might even call this first one C1 and the next one C2. But they only ask us in the question to use this plain old C to represent any constant. All right, so we have now y plus 3 equals, a constant multiplied. So again, I'm showing this e to the c as another constant times e to the x cubed plus 2x power, and then subtract 3. And there's your solution in explicit form, right? Y is, described as a function of x explicitly. You have solved for y. So c times e to the x cubed plus 2x power, and then, minus 3 after, right? Subtracting that 3, and there we go. Here's the, again, what they would call the explicit solutions to the differential equation. Y is solved for. Not always easy to do. Not always easy to get y alone. But for a lot of these problems, they are going to ask us for this. So this is what I'm going to type in into the assignment. So y equals, and some constant times e raised to the x cubed plus 2x power, and then down below, minus 3 afterwards. Great. Again, please read through the answer explanations. All right, moving on. All right, so we're back to now this here. They don't need us to solve the equation. They just want us to get to the point where you are integrating both sides. And we're just asked to fill in the integrands. All right, so again, we have y prime equals some polynomial with x and y in it. I will factor this polynomial to show you how it is indeed a separable equation. Then we'll do the separation and set up the integration. We have y prime equals 15xy plus 5x plus 24y, that's the 24y, sorry, plus 8. All right. So we have dy over dx. Again, if I'm going to see it as separable and do the separation of variables later, going to write the derivative in this differential form first. And then this over here, the first two terms have 5x in common. And then you'd have 3y plus 1. And then these two terms have 8 in common times 3y plus 1. So both of these have 3y, both halves have 3y plus 1 in common. So I'd factor that out. And then you'd have 5x plus 8 as the other factor. And you can double check by foiling, multiplying these, and you would get these four terms back. So now I have my function of y times function of x equals our first derivative here. This is definitely separable. And then we gathered the stuff with y on one side, so I'd have 1 over 3y plus 1, divide by the 3y plus 1 to get it on the left side with the dy. And then move the dx over to the right side with the 5x plus 8. There's your separation of variables. And then we would do integration, indefinite integration on both sides to try and, state the solutions. Or after the integration, we'll have the implicit solution, the implicit form of the solution, where y is implied to be a function of x. And then we could, if we wanted to, try to go about solving for y, get y as an explicit function of x. But for this particular problem, all we're asked to do is fill in the integrands, one of these things that I've just circled here. So on the left side, the integral with respect to y, we've got 1 over 3y plus 1. And the integrand with respect to x, on the right side, I have the integral of 5x plus 8. And that should be enough. That's all they want. Great. All right, moving on. All right, so again, we're asked to use separation of variables to solve this differential equation. Now, we don't have to do any factoring this time. It's already in the form of a separable equation. So the left side is y prime, which again I'll write in that differential form, right? dy over dx. And then you have your function of y times your function of x, right? Or function of x times function of y, whatever. So I can separate these. Now, I'll leave the 9 over here with the cosine of x. Constant multiples aren't going to hurt anything. I'm just going to move the y to the left side. So we'll have 1 over y dy equals 9 cosine of x, and move the differential of x over to the right side with that function of x. Now that I've separated the variables, we'll do our indefinite integrals of both sides. Left side, natural log of the absolute value of y. Right side, 9 times the sine of x plus some constant, right? And again, you only need to throw the constant on one of these sides. There's the implicit form of the solutions, but we can easily solve for y here by exponentiating, right? Y is going to be equal to e raised to this power, this 9 sine of x, plus some constant power. But as we saw in a previous example, this is the same thing as e to the 9 sine of x power multiplied by e to the c. Right, we saw this earlier. E to the c is just another constant. So because it's really any arbitrary constant here, I'm just going to call this c again. All right, even though it's a different C than the C earlier, if you want to use C1, C2, that's fine, but they do want just a plain old C in the final answer. So my final family of explicit solutions to this equation, y equals, any constant times e to the 9 sine of x power. And there we go. And I haven't really been checking my solutions, but if you'd like to check, take the derivative of this, put it on the left side, and then take this expression, put it on the right side for y here, and you'll see that both sides are indeed the same expression. This should satisfy the equation we were given. All right, so let me type this in. So y equals some constant times e raised to the 9 sine of x power. Great. Okay, moving right along here. All right, so once again, we saw an example like this as well earlier. I'm just asked to enter the integrands. I'm just going to say this one. I don't need to write this out. You see how this is already set up to where you can tell right away that it's separable. You have y prime equals some function of x times some function of y. Well, I'm going to put the function of y underneath the dy over here on the left and move the dx to the right with 2 minus 5x squared. So with the dx on the right side, you'd have 2 minus 5x squared. And then with the dy, you'd have, 1 divided by 7 minus 5y. 1 divided by 7 minus 5y. And that would be that. All right. Then you'd integrate and solve for y if you could. That would be the setup for finding the solutions to this particular differential equation. Yeah, very, very easy, that one. All right. All right. And once again, we're given one more last to just enter the integrands. But this time, like in a previous example, we have to see how this is, separable. It's not in that separable form just yet. So I need to factor this expression on the right. Right, so we have, y prime equals 8x squared y plus 2x squared plus 16y plus 4, which would factor, the first two terms have 2x squared in common. The second two terms have 4 in common, so you'd have a 2x squared plus 4, as a factor of this. And then the factor that the halves would share, if you pulled 2x squared out of the first two terms, you'd have 4y plus 1. And, both of these would have a 4y plus 1. So you have your other factors, 4y plus 1. And then you have, dy dx equals this. So separating the variables now, right, you got 1 over 4y plus 1 with the dy on the left, and then moving the differential of x on the right, you got your 2x squared plus 4, dx on the right side. And to go about solving this, we then integrate with respect to y on the left and with respect to x on the right. But like previous examples, though, all they're asking for are these integrands, right, that I just circled. So on the left with the dy, we got 1 over, 4y plus 1. On the right, the integrand with the dx, 2x squared plus 4. Wonderful. All right, so it looks like that objective's finished. Great. Keep moving. All right, so this time we're actually asked to solve. All right, go about and actually find the explicit solution. Y equals some function of x. All right, so I'll write out the equation. We'll do the variable separation, integration, and then solving for y. All right, so we have dy over dx, right, the first derivative of y. And it's very nice, this one, because it's already set up as an easily recognizable separable equation. Right? You have a function of x times a function of y. And now I can do this separation of variables. We'd have 1 over y minus 3 with the dy on the left. And I move the dx over to the right side with the 8x minus 5. Now we integrate. After the variable separation, I do the indefinite integral of both sides. Left side, I have the natural log of the absolute value of y minus 3. And then the right side, we have 4x squared minus 5x. And like I was saying before, you can put plus constant on both sides, but really it's unnecessary because you can just subtract a constant and get a constant on just one of the sides. So I like throwing it on the side with the x's, with the independent variable. So plus some constant. E to both sides, right? You have y minus 3 equals e raised to this 4x squared minus 5x plus c. Remember from earlier examples, e to the c power, right? E to the c power is another constant, so I'll just call that c as well. So we'd have a constant, times, that's like the e to the c is a constant, and then 4x, 4x, e to the 4x squared minus 5x power. And then I'm just going to add 3, to get y alone and have the explicit form of the solution set. And here we go. All right, this is what I'm going to be typing. Y equals, some constant c times e to the 4x squared minus 5x power plus 3. So y equals c times e raised to the 4x squared minus 5x power plus 3. Wonderful. So another one. And again, they want us to solve for y, right? Get the explicit form of the solution. So I'll write the equation out, and we'll do the separation and then integration, and then solve for y. So I got y prime equals 5y squared times the natural log of x. So if I divide, I'll keep the 5 on the right side. I'm just going to move the y squared over, so we'll have, y to the negative second on the left with the dy. And I'm writing it that way because we're going to use power rule here, reverse the power rule when I integrate. Equals, and then just, 5 times the natural log of x. And then, I put the dx over here. If this is dy over dx, try to move the dx to the right side. All right, so now comes the integration. Now, this integral on the right side involves the integral of the natural log function, which you can do by parts, but I have done in several videos now recently. There's the section 3.1 video on integration by parts. I also had several of these integrals of the natural log function in the section 4.1 video on a basic introduction or basics of differential equations. So you've seen this several times. So you could do this integral of the natural log of x function by parts, but this ends up being, x times the natural log of x minus x, plus some constant. This is something I remember, and I'm going to use it. All right, so left side would be negative y to the negative first, right? So negative 1 over y, right? Negative 1 over y, or y to the negative 1, equals, and then 5 times this, so 5x natural log of, I'm just distributing the 5 to the x log x minus x. So 5x times natural log of x minus 5x, and then, plus some constant. I can multiply everything by negative 1. So we have 1 over y equals, and that would make this, positive 5x, this middle term here, then minus 5x times the natural log of x, and then minus a constant. But that's just a constant again. So I'm gonna remember, if I do minus a constant, that's still a constant. So I'm gonna call that c again, or just plus c. All right. I know it sounds silly, but plus c minus c, right? It's all constants, that last term. And then to get y alone, I just flip both sides, right? I just need, I can multiply by y, then divide by this expression, or just take the reciprocal of both sides. So we'd have y equals, 1 over this expression here, 5x minus 5x times the natural log of x, and then plus some constant. And there we go. This is what I'll be entering. So y equals 1 over 5x minus 5x natural log of x, and then plus some constant c. Great. All right, so moving on. So another one, where we're solving separation of variables. So again, I separate the variables, integrate, solve for y. Same thing every time. All right, so this equation, y prime equals, and it's negative, e to the 3y power divided by x squared. So this is easy to separate. I'll divide by e to the 3y. That'll give me e to the negative 3y on the left with, again, I'm calling this dy over dx. So that'll give me e to the negative 3y on the left side with dy. Moving the dx over, I'd have negative, 1 over x squared, which is, x to the negative second on the right with the dx. So there's your separation of variables. Integrate. This side here would be e to the negative 3y, but then times negative 1/3, right, to reduce the chain rule. So negative 1/3 e to the negative 3y equals, and then over here, this would be x to the negative 1, times negative 1. So this is 1 over x, right? X is just x to the negative 1. And then plus some constant. So if I multiply, I'm going to try to get y alone here. I'm going to multiply both sides by negative 3. All right, times negative 3, and that'll be both of these terms over here. So that'll give me just e to the negative 3y on the left. And then I'd have negative 3 over x. Now, minus 3c. But like I've been doing in several of these examples, this here is a constant. So I'm just going to call it c plus c. So we have e to the negative 3y equals, negative 3 over x plus some constant. All right, again, I know it might be confusing to see all the C's if you like, again, if you want to call this first C C1, and then when I make a replacement, call it C2, and then if I make another replacement, call it C3, but they're all just constants. All right, and they do want in the final answer any constant, right? Any term that's just a constant to be represented by just a plain old C. Okay, now the natural log of both sides, you have negative 3y equals the natural log of this expression on the right, negative 3 over x, plus some constant, and then times negative 1/3. Right? So we finally get y equals negative 1/3 times the natural log of, and I'll just write this as c minus 3 over x. Right? And this is what I'll type in. So y equals negative 1/3 times the natural log of c minus 3 over x. Great. All right, so they have it written a little differently, but no biggie. All right, it's equivalent. Great. All right, so yet again, I'm asked to find the explicit general solution to this equation. So I'll say it again. We separate the variables, integrate, solve for y every single time with these. And they got to be these separable equations, of course, right? If you go on and take a course in differential equations later, you'll see plenty of differential equations that are not separable. So you got to go about trying to solve them some other way. Anyway, we have y prime equals, negative. We have negative, the opposite of some fraction here. The numerator of this fraction has 5x to the fourth minus 5 divided by, and then 4y. All right, so I'm going to multiply by negative 4y. Negative 4y over on the left side with the dy. And this is dy over dx, the first derivative here. And then move the dx over on the right side with this 5x to the fourth minus 5 numerator, right? All right, so now the variables are separated. We integrate. Left sides, they're both just polynomials, right? So negative, 2y squared on the left, and x to the fifth minus 5x plus some constant on the right. Multiply everything by negative 1/2. So I'd have negative 1/2 x to the fifth plus 5/2 x. And then we'd have negative 1/2, negative 1/2 times some constant. But again, this is just a constant, right? So I'm just going to put plus c again. I know, again, hopefully that's not too confusing. It's just another constant. And then I'll do the square root of both sides. All right, now I know that technically we should have, plus or minus. Um, when after integrating here, right, this is the implicit solution right here. This is our implicit solution, where y is implied to be some function of x. Well, could be one of two, one positive or negative square root of this expression here. I'll put the c in front, c minus 1/2 x to the fifth plus 5/2 x. And we'll just take the positive one. All right, they didn't say anything about any restrictions, so let's just take the nice one for now. If there were other restrictions being made, perhaps you would have to use, look at just the negative square root of this, but I'll use the positive one, right? That'll make it nice and clean. Because again, they didn't mention anything about any specific restrictions being made on the value of y. So I'll just use the positive one. So y equals square root of, and then I have c minus 1/2 x to the 5th, then plus 5/2 x, all inside the square root there, mind you. Great. All right. Now you see they have the plus or minus. Probably mentioned something about it down here. Yeah, see, since no initial condition has been given, no substitutions are needed. Right, so, oh, that's just if you have to find C. But still, no initial condition was given. So if they gave me some initial condition, say the value of y had to be negative when x was 0 or when x was 1 or something, then I'd use the negative square root. Right? I'd look at that function. But if I was given a condition where y had to be positive when x was some value, well, then I would look at the positive square root. All right, so it looks like they're taking the plus or minus symbol, so that's nice. But because there was no restriction given, I just said, okay, positive 1 for now. All right, just 1. Okay. All right, so it looks like that objective's done. Hooray. So we got 2 more in the other heading, right? So now we're in this other heading, the other bold heading here. We got 2 more objectives. All right, so this one, solve differential equations application problems using separation of variables. So anytime you see the word, application problem, those words, it's, word problems. So they'll have different types. If you read through the instruction or read through whatever text you have here, I believe they're working out of the openstacks.org. That's stacks with an X. Openstacks.org. Their Calculus 2 or Calculus Volume 2 text. And if you go to their section 4.3 on separable equations, you will see what applications may come up. There's Newton's law of heating and cooling. There's mixture problems, radioactive decay, exponential growth, decay, those kinds of things, where a separable differential equation may occur in the solving and in the modeling and solving of the problem. So let me read through this. We have a patient is treated for a bacterial infection in a hospital and is prescribed to take an antibiotic in pill form. Each pill contains a dose of 500 milligrams of antibiotic. The antibiotic's rate of clearance from the bloodstream is characterized by the constant K equals 0.0990, over hour. That's one per hour. Using the differential equation. All right, so they give us a differential equation here. How kind of them. We don't have to model this ourselves. So using the differential equation, y prime equals negative ky, where they gave us the value of k, this 0.0990 per hour, where y is the amount of antibiotic in milligrams in the bloodstream at, any given time, right? Because it looks like we have time here, hours. Find the amount of antibiotic that remains in the bloodstream, 10 hours after the patient takes the pill. Round your answer to 2 decimal places, right? So I'm going to be entering this into a calculator. I will just be going to that desmos.com free online calculator for this. So yeah, let me write this out and all the information we were given. Now, like a lot of problems, very often it helps to start general, work through things in general first, and then go to a specific situation. You saw that a lot in Calculus 1 with related rate problems or optimization problems, right? Where it helped out a lot to start off in general and then look at, the specifics, the specific situation you were in. The equation we're given here is, y prime equals k times y, where y is a function of time, right? So I'm going to use t for time, and y of t represents the amount of antibiotic in the bloodstream at time, I'll just say at time t, at t hours. And this amount of antibiotic is in milligrams, right? And T is time in hours, right? And K is a constant. They told us what that constant was. I'll put it in later. All right, what's that 0.0990 per hour? I'll put that in later. All right, so y prime here I can think of as dy over dt. And then we can do a separation of variables. Divide by y, you get 1 over y times dy. And move the dt over here with the constant, and you got q dt. There's your separation of variables. Integrate. Left side, you got the natural log of the absolute value of y. Right side, we have k times t plus some constant. E to both sides, y is equal to, now remember, e to the c power is just another constant. So I'll call that c times e to the kt power. Right. So here is the solution, the general solution to an equation like this. Y is going to be some constant times a nice exponential function. Now, the information we're given. So I found the general solution to any equation like this first. Now let's go to some specific info. What were we given specifically about this particular antibiotic? So it said early on that each pill contains a dose of 500 milligrams of antibiotic. So initially, I mean, we would like eventually, I mean, okay, so initially, right, at time 0, when the person takes the pill, oh, I miswrote the equation, didn't I? My apologies. It's y prime equals, negative ky. I was wondering, like, it looked to me like this thing would be increasing. So all that's going to change here, I'm sorry, it should have been y prime equals the opposite of ky. So this will be negative, this will be negative, this will be negative. Okay, so that'll be a decrease, great. So initially, right, this pill contains 500 milligrams of the drug, right? So we got y of 0, let's say, is 500 milligrams, right? This, you initially have this 500 milligrams of the antibiotic inside you, and then it starts slowly dissolving away, right? The amount decreases over time, of course. That's why it should be minus k, not k. Yeah, something looked a little fishy. That's why I was kind of hesitating. Then I looked back and, oh yeah, it should be y prime equals negative k. So let's use this. I can use this piece of information to find this c, right? Because this is saying when t is 0, y is 500. So running through my model here, we'd have 500 for y on the left equals c times e to the 0, right? T is 0, so 0k, 0 times whatever is 0. E to the 0 is 1. So that gives us the c. So now I go back, we got this now. Y equals 500 times e to the negative, and then k was that 0.0990 number they mentioned in the problem. I'll put that in here as well. So 0.0990 p. So here's the model, right, for this amount of antibiotic after so many hours that's left over. They want how much antibiotic is left after 10 hours, right? So I'm replacing t with 10, which will just move the decimal place on this to the right one. So we'd have 500 times e to the negative 0.990, and that would be milligrams of antibiotic left. So if they wanted an exact answer, this would be it. But they want us to round this, to what? They want us to round to 2 decimal places. So I'll go to that Desmos calculator. This is again desmos.com. I'm going to enter 500 times e raised to the negative 0.99. And that's approximately 185.788, which is 5 or more, so 79 milligrams. 185.79. That is what I shall enter back here. 185.79 milligrams. Wonderful. And again, please look through, the answer explanations. So you see again how they go general and then specific. All right. Okay. All right. So the other objective that hasn't been touched yet, pardon me, find particular solutions to differential equations using separation of variables. So these are your initial value problems. You may recall these from section 4.1's video on the basics of differential equations. Yeah, initial value problems are, you have a differential equation and then you have some sort of condition that the solution has to meet. So your final solution shouldn't have any unknown constants in it, right? You're trying to find the value of those constants that will satisfy the condition. So like here, we're asked to find the particular solution for the differential equation below. I got this thing with all the trig functions in it. And we're given the following condition. The value of y when x is pi over 4 must be 0. So I will write out this initial value problem, right? This differential equation with conditions. So here's the equation. Y prime equals, got 4 times the cotangent of 2x times the cosecant of 2x, and then divided by the sine of 2y. And then your condition is the value of y when x is pi over 4 must be 0. All right. So this is, y prime here. Again, I'm thinking of this as dy over dx. And we'll do our separation of variables. I'm going to multiply by the sine of y, or sine of 2y, sorry. So you got sine of 2y dy on the left. And then this numerator has nothing but x's in it, and I'll put the dx with that. So you got 4 times, and then I'm going to write this in a way that's probably more familiar to you from Calculus 1. It's cosecant of 2x times cotangent of 2x, and then with the dx, right? So I've done the separation of variables. Now we do our indefinite integral. Left side, remember the antiderivative of the sine of something would be negative cosine of that thing. So negative cosine of 2y, but then times a half to counteract that 2 there. So negative half cosine of 2y on the left side. And then you may recall cosecant of something times cotangent of something, right? Cosecant theta, cotangent theta. Well, that was just, the opposite of the derivative of cosecant theta. So this right side will be 4 times, and then, the opposite of, I'll put a minus here, cosecant of 2x. But then again, you got the 2x here, so I got to multiply by a half to counteract that when I anti-differentiate. So that's negative 2 times cosecant of 2x, right? Again, the derivative of cosecant 2x would be negative cosecant 2x, cotangent 2x, times the 2 from inside, right? So you'd have positive 4. Yeah. And then plus some constant, of course, right? Right, so what I'm going to do now is multiply both sides by negative 2. Right, this side here by negative 2, and this side here by negative 2. All right, and I'll just distribute the negative 2. So the left side is just going to be cosine of 2y equals, and then negative 2 times negative 2, positive 4 times the cosecant of 2x. I've been doing this a bunch this video, right? Negative 2 times c is negative 2c, but that's just another constant, right? So again, I'm just going to say plus c again. All right. Now I could continue on and solve for y, and we're going to have to eventually. But I personally, when I'm given an initial value problem, especially with these separable equations, after integration, right, when I get the implicit form of the solution, I'll use the condition now, find c, and then once we've found c, I'll go and solve for y. Right, so we are told, again, when x equals pi over 4, y equals 0. So I'm going to use that information here. So replace y with 0, x with pi over 4. So, and then we can solve for the constant c here. All right, so the cosine of 2 times 0 equals 4 times the cosecant of 2 times pi over 4 for x, plus some constant. Now the left side, we have the cosine of 0. Remember that was 1. Then the cosecant of 2 pi over 4 is pi over 2. And the sine of pi over 2 is 1. So the cosecant's the reciprocal, that's also 1. So this is 4 times 1, that's 4, plus c. So c is negative 3. So I'm popping that in up here. And we get, oops, sorry, 4 times the cosecant of 2x, and then minus 3, right? Plus some constant, plus c. The c is negative 3. So I have the cosine of 2y equals this, 4 cosecant of 2x minus 3. Then I'll just say what's happening, skip to the end. To get y alone, I'd have to take the inverse cosine of both sides and then multiply by a half. So when all's said and done here, y equals half of the inverse cosine of this expression, this 4 cosecant of 2x minus 3, right? So I know that's kind of tiny there, but this is half of the inverse cosine or arc cosine of 4 cosecant of 2x minus 3, all inside the inverse cosine there. And that's what I'm going to be typing. That function of x would satisfy the initial equation and the initial condition. So back here, y equals 1/2 times, I'll just do arc cosine, ARC COS for inverse cosine of, and then inside that inverse cosine we have 4 times the cosecant, CSC of 2x minus 3, close all those parentheses there. That should be good. Wonderful. All right, so we're back to another one of these. I want to find a particular solution that satisfies a condition. This time the condition is, the value of y when x equals 0 is 9. And we have this equation. Right, so again, I'll write this initial value problem out. And solve it, using separation of variables. So here's the equation. Y prime equals, 8x plus 1 times y plus 8. And then the condition, y when x equals 0 must be 9. All right, so easy to separate this one. We have 1 over y plus 8 with the dy on the left, and then moving the dx to the right. 8x plus 1 with the dx. All right, integrating. All right, we have the separation of variables. Now we do our integration. Got the natural log of the absolute value of y plus 8 must be equal to 4x squared plus x, and then plus some constant. Now here's where I'll use the condition to find the constant. Now the constant, when x equals 0, the right side is just the constant. Right? You'd have 0 plus constant plus c. Y equals 9. 9 plus 8 is 17. The absolute value of 17 is 17. You just have the natural log of 17 on the left. So there's your constant. So this is 4x squared plus x plus the natural log of 17. And now if I'm going to solve for y here, exponentiate both sides, we'd have y plus 8 equals e to this power. Remember, that'd be e to the 4x squared plus x times e to the log of 17. The e to the natural log of 17 is just 17. So I'd have 17 times e to the 4x squared plus x power. And then, of course, subtract 8 to get y alone. Right, so y equals 17 times e to the 4x squared plus x power, and then minus 8. This function here would satisfy the differential equation and the condition that we were given. So y equals 17 times e raised to the 4x squared plus x power, and then minus 8 after. Wonderful. All right, continuing on. All right, so here we have another application. This one involving temperatures and specifically Newton's law of heating and cooling, or Newton's law of cooling, which I'll describe when I go to my paper. So, yeah, so a pie is removed from the oven after baking thoroughly, and the temperature of the oven is 375 degrees Fahrenheit. The temperature of the kitchen is 70 degrees Fahrenheit. 15 minutes after taking the pie out of the oven, its temperature is 225 degrees Fahrenheit, right? So it went from 375 when it was pulled out to 225 degrees, 15 minutes later. We want to wait until the pie has cooled to 80 degrees Fahrenheit to cut and serve it. How long will we have to wait? All right, so like I said, this involves something called Newton's law of cooling, which I'll describe here. You could say heating and cooling, but so here's the differential equation that's coming of this, the model for a problem like this, where you have an object that is a certain temperature and it is surrounded by an atmosphere that has its own temperature. And if the atmosphere is cooler than the object, the object will cool. If the atmosphere is warmer than the object will warm. Right? So here's how. So here's the equation. You have d capital T over d little t, and I'll explain what all the letters mean, the big T, the little t, in a second, is equal to some constant A times the quantity capital T minus, and then capital T sub 0, right? Or maybe they were calling it T sub A. I've also seen other books where they call it T sub M. I'll call it T sub A actually, not T sub 0, because that might be a little deceiving. So let's call this T sub A. All right, so let's see what all these mean first, right? So little t, right? Little t is the time, and it could be time in minutes or hours or days or months, right? So it depends on the problem. So here in our example, this is going to be time in minutes. Right, so little t is time, and capital T is going to be a function of little t, right? Depends on little t. Capital T represents the temperature of the object that we're describing. So in this particular problem, it was this pie, where a pie was removed from an oven and left to cool. So it'll be the temperature of this pie at time t. Right? And then the K is just it's a constant of proportionality. So what Newton's law says is that the speed at which the temperature changes, right, the rate at which the temperature of the object changes over time is directly proportional to the difference between that object's temperature and the temperature of the atmosphere of the surroundings. So you call this TA, TS for surroundings, TA for atmosphere, TM for medium, the medium the object is in, whatever. So that's what this T sub A in my equation up here represents. This is the temperature of the atmosphere that the object is in, or the temperature of the surroundings. And this is, for our purposes, a constant. So they mention this kitchen. The pie is put into a kitchen, taken out of an oven and put into a kitchen that is 70 degrees Fahrenheit, and that will not change. All right. So this is the temperature of the, again, I'll call it the atmosphere slash surroundings. Now, in real life, this is more than likely not going to remain constant, but for our purposes, like I said a second ago, we're going to assume that this is a constant temperature, like the temperature of this kitchen being 70 degrees. All right, so I'm going to go through like I did before with the application, the last application example. And we're going to start in general and then work to specifics. So again, K here is constant, this TA is constant, so the only variable that's really being worked with here is capital T. I mean, there's also a little t, but there's nothing else really with little t in it. So I'll do a separation, get all this stuff with involving capital T on the left. So I divide by this capital T minus TA, and then move the dt over to the other side, with the constant, the little t. Now I have my separation of variables, so we integrate. Left side's a natural log, natural log of the absolute value of, capital T, the temperature of the object minus, the temperature of the atmosphere. And over here, you just have, K times little t, a constant times little t, constant times time, plus some constant. And I'm going to solve for capital T. Right? Capital T was like y in earlier things, where that's the dependent variable, and the independent variable is time. Exponentiate. So you get capital T minus t little pa. Remember, when I do e to the kt plus c, e to the c is just a constant again. So that's some constant times e to the kt power. And then to solve for capital T, I add the temperature of the atmosphere. So T of little t, right? When I solve for capital T, I'm getting some constant times e to the kt power plus, pardon me, the temperature of the atmosphere. So here's the general solution to an equation, that's modeled by this Newton's law. So now that I have the general, let's go to the specifics for this problem and plug some of this stuff in. So they told us the temperature at time 0. So this is the pi. Capital T represents the temperature of the pi. So the temperature of the pi, when we initially pull it out of the oven, it's 375 degrees Fahrenheit. We were also told the temperature of the atmosphere. Now this is the temperature of the kitchen, right? The thing, the area surrounding the pie. They told us that this was 70 degrees Fahrenheit. Then they said 15 minutes later, 15 minutes after taking the pie out of the oven, the temperature of the pie is 225 degrees Fahrenheit. So T of 15, again, 15 minutes, 225 degrees Fahrenheit. And again, this is the temperature of the pie again. So they gave us all this information. I can use this stuff to find C and K. If I can find this constant C and this constant K, then, and we already know TA is 70, then we can answer any question they want. All right, so the first thing, T of 0, the initial temperature of the pie is 375. So 375 will be on the left for capital T, the temperature of the object, temperature of the pie, equals C times E to the 0 K, right? K times 0, plus, and then temperature of the surroundings was 70. Now E to the 0 is 1, so this is just C plus 70 over here. Subtracting 70, we get 305 is the value of this constant. Okay, so now we have this. Now we have the temperature of the pie times T after 2 minutes. It's 305 times E to the KT power plus 70. Now I just need to find K. And that'll be where this piece of information comes in. When T is 15, little t, when time is 15 minutes, big T is 225. So I'll plug that information in and we should be able to find little K, right? So I have 225 on the left, right? That's for capital T, the temperature of the pie, equals 305 times E to the K times time, so 15K, and then plus 70. Well, if I want to solve this for K, I'm going to subtract 70. I have 155 on the left equals 305 times E to the 15K. Divide by 305, right? So I'll have E to the 15K equals, 155 divided by 305, but this will simplify. Right? This is 5 times 31. This is 5 times 61. So 31/61. Then take the natural log of both sides. You got 15K equals the natural log of 31/61. So this should be some negative number. And then times 1/15. So K is 1/15 times the natural log of 31/61, which I will write this way for reasons I'll make clear when I put this back into the equation. The 1/15 as the power inside, remember the power property for logarithms. So it's the natural log of, 31/61 to the 1/15 power. So there's the value of K. I could enter this into a calculator and get some value for it, but I'll save it to the end. Right? I'll save the calculator to the very end when I find the answer they want. All right, so I pop this in for K. So now we have the temperature of this pie at time T. It's 305, right? That was the value of that C times E to the KT. So T times this natural log of 31/61 to the 1/15 power. And I'll also put the T as in with the 1/15. So this will be the natural log of 31/61 to the T over 15 power. And then the log and exponential will undo each other. And then we have plus 70. And so again, the reason I did that is so I could do this. So the temperature of this pie at any given time after I pull it out of the oven and leave it in this 70-degree kitchen is this 305 times, then here I'd have E to the natural log 31/61 to the T over 15 power. So the E and natural log undo each other. And I'm left with just 31/61 to the t over 15 power. All right, and then plus 70. And there we go. This isn't the answer yet, but this is important. All right. I mean, I could have used this as well. I mean, these are the same thing. But now I have an equation. I have a function that tells me how hot this pie is at any moment. Finally, now that I have this equation, I have this function, I can answer their question. They asked, how long will we have to wait until the pie has cooled 80 degrees Fahrenheit, right? So the question is, when is T of T going to be 80 degrees Fahrenheit? So when is capital T 80? So I'm going to put in 80 for big T, and we're going to solve for little t. So 80 over here equals, 305 times this 31/61 to the T over 15 power plus 70. Take away the set. I want to get this base and power alone. All right, isolate this, and then we'll use logarithms. Subtract 70, you got 10 equals 305 times 31/61 to the T over 15 power. Then divide by 305, right? So 10 over 305, which is the same as 2 over 61. And this is 5 times 2. This is 61. 2 times 5, 61 times 5. And this is equal to 31/61 to the T over 15 power. Do the natural log of both sides, right? So a natural log of 2/61 equals, and when I do the natural log of this side, I can pull the power out. This will be T over 15 times the natural log of 31/61, and then multiply by the reciprocal of this, multiply by 15 over the natural log of 31/61. So T is the natural log of 15 multiplied by 15. 15 times the natural log of 2/61, divided by the natural log of 31/61. All right, and then we're asked to round this to the nearest minute. Now t was in minutes here, so I'm just rounding to the nearest whole number. So let me enter this into a calculator. This is from an earlier problem. 15 times the natural log of 2/61 divided by the natural log of 31/61. So 75.7. So rounding to the nearest minute, that'd be 76 minutes from the time we took it out of the oven. And that's what I'll enter here. Right. So a lot involved there. But if you probably saw something like this in Calc 1, maybe even in the pre-calc course, not with the differential equation, mind you, but this is very much an exponential growth or exponential decay type problem. So if you recall solving or modeling situations like that, exponential growth, exponential decay, this is very similar, practically the same kind of a problem. Okay. All right. Now let's talk again, just another initial value problem given a differential equation with some condition. Find the solution, the particular solution to this. So here's the equation. Y prime equals the natural log of 8 x to the fourth divided by 4x. And the condition is the value of y when x equals 1 must be 0. Now this, you'd have 1 dy and then move the dx. All this has x in it. There is no function of y over here. So I just put the x. Technically it is separable, but this is really like any other the equations you saw in section 4.1. But this is y prime in terms of x. So to find y in terms of x, you're just integrating. We have the natural log of 8x to the fourth, over 4x dx here. And then, yeah, to get y, right, you're just integrating. Right? Y equals. Now, integrating this, I'm going to do the following u substitution. I'm actually going to have u represent the numerator, the natural log of 8x to the fourth. Again, it's just something I recognize here. Then du would be, remember the derivative of the natural log of something is 1 over that thing, right? So 1 over 8x to the fourth, but then times the derivative of the thing inside, right? So times 32x cubed dx. Well, if I do some simplification here, 8 goes into 32 4 times, x cubed over x to the fourth would be 1 over x. This is 4 over x dx. Well, do you see the dx over x? So dx over x would be a quarter du. And in the integral here, there's dx over x. So that's going to be a quarter bu. So I'll have 16 in the denominator. And I can pull that out at 1/16 times the integral of. And then I call this whole numerator u. And I pulled the 1/16 out. And then you have, just u du. And so this is 1/16 times, half u squared, so 1/32 u squared. And now I'll sub back, remember what u was this thing. So y equals, 1/32 times, and then u squared. So I'll put this, natural log of 8x to the fourth, that thing squared. Now, sometimes you might see the square after the log, with like a trig function. But I'd be careful here. Some computer programs, I don't think Knewton will accept that. So you may have to put the parentheses around the log here like this with the square outside. It accepts it with the trig functions, right? If you got sine squared, cosine squared, tangent squared, it'll take those. But with the logs, I'm not quite certain if it actually takes them. We could type it in and see, but I'm just going to be safe and leave it like this. And then plus some constant. Don't forget, right? So y is this plus some constant. But then we're trying to find a particular solution, right? We need to satisfy this condition up here. When x equals 1, y must be 0. So put in 0 for y equals, 1/32 times, and then the natural log. Now x is 1, so this would just be 8 in here. And this is being squared, and then plus some constant, right? Now the natural log of 8, you can leave it like that, say c would have to be the opposite of this, right? To subtract this. But I see something here, right? Natural log of 8. 8 is 2 cubed, and you can pull the 3 out. 3 times the natural log of 2. And then this is being squared. That'd be 9 times the natural log of 2, to the second power. And then we have times 1/32, right? So c would be the opposite of 9/32, times the natural log of 2 squared, right? So there's your constant. And that's going to go in here, right? So we'll have y equals 1/32 times the natural log of 8x to the fourth, that quantity squared, minus, 9/32 times the natural log of 2 squared. Yeah, it's a lot to type, but it does satisfy our condition. Okay, so y equals 1/32 times, and then the quantity, natural log of 8x to the fourth squared, minus, we got down there, minus 9/32 times the quantity natural log of 2 squared. And that should be good. Oh, what happened? All right, I'm going to double check my work here and see where I made a boo-boo. So I'm not really seeing my mistake. So it may just be in the notation here. So I'm going to get rid of these parentheses. Let's see what happens. Oops. Okay, let's do this. So I'm going to actually just get rid of that and say, all right, do natural log of that squared. So we have 1/32 times the natural log of 8x to the fourth. Maybe if I just type it twice to avoid any confusion. So natural log of 8x to the fourth times itself. And then minus 9/32. And then we had natural log of 2 squared, so I'll do natural log of 2 times the natural log of 2 again. Let's see if that works out. Because, yeah, I'm not really seeing where I went wrong. I don't think I would. I'm looking through my calculations and nothing seems incorrect. Not quite right. Okay, so you see it's the notation. Remember I said natural log of 8 was, natural log of 2 cubed, pulled the 3 down, made that 9/32 times natural log of 2 squared. So it is the notation that I missed. So they're putting this, so I had an extra set of parentheses. See, like, look at this. I had the natural log of 8x to the fourth, and then that squared. They got that here, times 1/32. Minus, and then again, this natural log of 8 is also 3 times the natural log of 2, so this would be squared. That'd be 9 times the natural log of 2 squared over 32. So what I had initially is correct. Why isn't it marked correct here? All right, well, I'm going to pause here and send some feedback to Newton. Yeah, look at down here. They're putting the parentheses again around it. I don't understand why my initial result was marked wrong. All right, so my apologies here. Again, this is something Newton related. So I'm sending some feedback just now. Give me a second. Pause the video. So I just sent some feedback to Newton. Hopefully they get back to me soon. Because like I said, there is no difference between what I have here. This is equivalent to what they're getting in their answer. All right, so I'll just understand that for any problem that comes up like this, and I will type it without the extra set of parentheses and don't simplify the log for some reason in the future. Right, so my apologies. I will leave a note about this in the description to the video as well. All right. So moving on, we got another initial value problem. Let's solve this equation and then make sure it satisfies the condition. And hopefully we don't have another issue with notation and little ticky-tacky parentheses, like in the last example. So the equation we're given, y prime equals, this is e to the 4x minus 5y power, which, if I want to see this as separable, would be e to the 4x divided by, e to the 5y. And I can easily separate. The condition, the value of y at x equals 0 is the natural log of 4. All right, so let's solve this, do the separation, get the e to the 5y on the other side, multiply by e to the 5y, so we'd have e to the 5y dy on the left, and take the dx to the other side, e to the 4x dx. Now I have the separation of variables, we're going to integrate. Left side would be 1/5 e to the 5y, right side 1/4 e to the 4y, or sorry, 4x, right, so with respect to x, and then plus some constant. And I'm just going to find the constant right now. So when x is 0, y should be the natural log of 4. So we have 1/5 times e to the 5 times the natural log of 4, right? Y is natural log of 4, equals, and then 1/4 times e to the 0. Now x is 0 here in the condition, plus some constant. Now this natural log of 4, times 5, put that 5 in as the power. This would become 4 to the 5th, right? 4 to the 5th power, which is 2 to the 10th, right? 2 squared to the 5th. So that's 1024. So e to the natural log of 1024, that's just 1024. So this side is 1024 over 5, right? Equals, and then a fourth times 1. E to the 0s is 1, so equals 1/4 plus c. So c is 1024 fifths minus 1/4. Need to get a common denominator, so I multiply this by 4 over 4, and this by 5 over 5. Now this would be doubling this again, so 2048, 4096 over 20 minus 5, so this is 4091 over 20 for the constant. Okay, so now we have 1/5 e to the 5y power equals 1/4 times e to the 4x power plus 4091 twentieths. Yeah, so I'll multiply everything by 5. E to the 5y equals 5/4 times e to the 4x plus 4091 fourths. Right, because I'm multiplying by 5 goes into 24 times. Natural log of both sides. So 5y equals the natural log of this 5/4 e to the 4x plus 4,091 fourths, and then times a fifth. All right, so let's do this, put the 1/5 in there. All right, that's 1/5. So y is 1/5 of this natural log. And this, yeah, this should work out, right? Because when I plug in 0 for x, it'd be 5 fourths plus 4,091 fourths. That'd be 4,096 fourths, which just cut in half twice. It'd be 1,024, which again, that's 4 to the 5th power. Pull the 5 out. That's the natural log of 4 when I plug in 0. So this satisfies our condition, and it should also satisfy our equation. Yeah, so 1/5 times the natural log of 5 fourths times e to the 4x power plus 4,091 fourths, and that's all inside the log there. And hopefully there isn't an issue like with the last example where there's a parentheses needed somewhere that I didn't put. Great. Yeah, so again, if you couldn't tell from my voice, I am still quite annoyed by that previous example. All right. So another one. Now, look at this. See, it says find the particular solution to this differential equation below with this condition. Note that your answer will only be an implicit solution. Only implicit. So that means don't solve for y. You don't have to try and solve for y here. Write the solution as a function of y on the left side of the equation and your function of x with the particular solution constant on the right. Okay, so they do want it in a specific way. So that was function of y, so just stuff with y on the left, and stuff with x and the constant that we find on the right. They don't want us to solve for y here, right? Just an implicit solution. So we have y prime equals 4x plus 4 over 2y plus 1. And the value of y at x equals 8 must be 2. So when I do separation of variables here, we're going to have, 2y plus 1 with the dy on the left, and 4x plus 4 with the dx on the right. We integrate. You got y squared plus y on the left side. And then 2x squared plus 4x. And then plus your constant on the right side with the x's like they wanted. Okay. So again, they're not asking us to solve this for y now, right? You have a quadratic in y. Now you could apply the quadratic formula and junk, but that'll be pretty complicated looking. So we're not doing that. And they're not having us do that. All right, so now I'm going to enter the stuff from the condition. When x is 8, y must be 2. So I have 2 squared plus 2 on the left equals 2 times, and then 8 squared plus 4 times 8 plus our constant, and we can solve for the constant. The left side is 4 plus 2, that's 6. The right side is we can factor 8 out of both of these, and then you'd have 2 times 8 plus 4, you'd have 20 times 8, that's 160 plus c, or you can 64 times 2 is 128, plus 32 is 160, whatever, and then subtract 160. So the value of the constant here is negative 154. So I'm just putting that here, right, minus 154. And this is all they ask us to enter, right, the implicit form of the solution. Don't actually try and solve for y. And this is the way they wanted it as well, right? They said have just some function of y on the left and a function of x with the constant on the right. Right? Notice in the answer here, there's no y equals, right? That's also a giveaway that you're entering an implicit solution. So y squared plus y on the left equals 2x squared plus 4x, and then minus 154 on the right. Right. Wonderful. Moving on. Okay, so this one I got to be careful with, right? And this looks very similar to that example I had earlier where the notation was funky, right? Um, so I'm going to be careful with this one, and I'll type it the way they had it and not actually simplify my log, all right? Hopefully the way I'm typing it's the way they want it. As annoying as that may sound. So equation and condition again. Equation y prime equals the natural log of 2x cubed over 3x. The condition y of 1 equals 0. All right, so again, when I do the separation here, I mean, this is only a function of x. So to find y, I'm just integrating that. That's integral of natural log of 2x cubed divided by 3x, dx, and very similar to that problem that we had the issue with earlier. I'm going to have u, substitute u for just the numerator here, be the natural log of 2x cubed, and then du would be 1 over 2x cubed times 6x squared, dx, that's just 3 over x dx, right? So dx over x is 1/3 du, right? So this dx over x that I have here, that's 1/3 du. So I got 1/9 that I can pull out. And this is 1/9 times the integral of, u du. So this is 1/18 u squared, and then I sub back. So y equals 1/18 times the natural log of 2x cubed. This time I'm just gonna type it with the square right after. Earlier I had the parentheses around it and squared it, and for some reason it wasn't giving it to me. And then plus some constant, right? Now I got to use this condition up here to find the constant. Now when x equals 1, y equals 0. So you got 0 here equals 1/18 times the natural log of just 2 squared, so, and then plus c. No need to simplify this, so c equals, negative 1/18 times the natural log of 2 squared. And once again, just to make sure that they're giving it to me correct, counting it correctly, I'm not going to do what I did earlier and put parentheses around this. I'll just leave it with the square after like that. All right, so this is going to go here, and then I'll enter this expression, right, without the extra set of parentheses. All right, let's see this. Hopefully this works out. So 1/18 times the natural log of, inside the log we have 2x cubed. And then after that log is done, I'm going to put the square. Okay? So again, no extra set of parentheses. Then the constant was minus 1/18 times the natural log of 2. And again, after the natural log of 2 has been entered, put the square without that extra set of parentheses like I had in that, again, that earlier example like this with the issue. Oh, perfect. Okay, so they don't want extra set of parentheses around the log. So if you're raising a logarithm to a power, just put that power after it. And I hope they get back to me with that feedback I sent, because that is annoying. Even if I put a set of parentheses around it and squared it, it should be the same, counted as the same. All right, so that's it for that objective. Hooray. All right, so the only thing left are those application problems, maybe like Newton's law of cooling, or, we saw that one with the antibiotics and stuff, right? Here's another one with this time instead of a pie, it's a cake, right? But it's still the Newton's law of cooling. All right, so I'm just going to I'm not going to write all of Newton's law of cooling again. So if you want to go back to that last example, it was the second problem we did in the application objective. If you want to go back to that and see how I, solved the differential equation in general for Newton's law of cooling, please do that. I'm just going to start off with the formula that you get after solving the differential equation. Yeah, so here a cake is removed from the oven after baking thoroughly. The temperature of the oven's 450, right? So that's the initial temperature of the cake. The temperature of the kitchen is again 70 degrees. That'll be the temperature of the atmosphere, that T sub A, I called it. 15 minutes after taking the cake out of the oven, its temperature is 300 degrees Fahrenheit, and we want to wait till the cake is cooled to 80 degrees. How long will we have to wait? All right, so this is basically the same problem as the pie problem. The only major difference are these initial temperature and 15-minute temperatures. Everything else is pretty much the same. All right. So again, I'm just going to write out the formula you get for Newton's law of cooling, right? So remember the temperature of the cake after T minutes is some constant C times e to some constant k times t power, little t is time, and then plus the temperature of the atmosphere. Now, the temperature of the atmosphere, that's the temperature of the kitchen. And again, they told us this was 70 degrees Fahrenheit, so I'm using 70 here. So we have the temperature of the cake after t minutes. It's some constant, times e to the kt plus 70. And I'll take one little piece of information at a time. We'll find the C, we'll find the K, and then we can answer their question. But first, we were told at time 0, right, when the cake was initially taken out of the oven, it is 450 degrees Fahrenheit. All right, so that leads me to this, capital T on the left here is 450 equals, and then, when I plug in 0 for little t, this would be e to the 0 times c, so it's just c plus 70. Let's take away the 70. This constant, then this c, it's 450 minus 70, so 380. Right, that's the initial difference between the temperature of the cake and the temperature of the atmosphere, the temperature of the kitchen. So now we have this, right? The temperature of the cake at any given time is, 380 times e to the kt plus 70. Now the next piece of information will help me find k, right? They told us after 15 minutes, so t of 15, the cake was 300 degrees Fahrenheit. So I put in 300 for capital T on the left, and equals 380 times e to the kt and plus 70. Oh, sorry, not kt, k times 15. So that'd be 15k. And then we can solve this for k. Right, so I take away 70. That'll be 230 equals 380. times e to the 15k power, divide by 380, that'd be 23/38, all right? The tens will cancel, equals e to the 15k. Then take the natural log of both sides. I'll do this over here. So we'd have 15k equals the natural log of 23/38. And so k is, 1/15 times the natural log of 23/38, which, you can punch this into a calculator, get a value for k. Now, when I plug this here, you'd have, t over 15, you can put that in as the power on 23/38, and you'd have e to the natural log of 23/38 to the t over 15, and then e and natural log will undo each other, so we have this after all that. We have t, temperature of the cake at any given time would be 380 times, and then 23/38 to the t over 15 power. You saw me do something like this earlier. So if you want to go back to that other example from the application problem objective where we were doing Newton's law of cooling, please see that again. And then plus 70. All right, so here's the model for our cake temperature. Then they asked, how long do we have to wait until the cake is 80 degrees? So I'm putting in 80 degrees Fahrenheit here. I'm putting 80 on the left for capital T. And then we're solving for little t. So I'd have 80 equals, 380 times 23/38 to the t over 15 power plus 70. Okay, so again, go back to that other example. I would get this expression alone, then take the natural log of both sides and, get little t alone eventually. So I'm just going to describe what's happening and not write every little step. All right, so I'd subtract 70. That'll give me 10 over here. Divide by 380. That'll give me 1/38. Do the natural log of both sides. And then you'd have t over 15 times the natural log of this. So I'd multiply this by 15 and then divide by the natural log of 23/38. And this will be t. All right, so there's how long. 15 times the natural log of 1/38 divided by the natural log of 23/38. But they do want us to round this to the nearest minute, right? So again, I'm going to enter this into the calculator, which this is actually the calculation from the earlier problem in this video involving Newton's law of cooling. I'm just going to change the expressions inside this log. So we have 15 times the natural log of 1/38 divided by the natural log of 23/38. So 109 minutes if I round it to the nearest whole minute. 109 minutes. A little under 2 hours we'd have to wait for it to be cold enough to cut and serve. Okay, great. All right, moving on. So this is like earlier with the amount of drug in the bloodstream. So the very first example we did in the application problems objective, very similar to this one. Maybe not exactly the same, but similar. So an emergency room doctor orders a drug to be administered to a patient intravenously, right, into the blood. The half-life of the drug is 5 hours. Now, half-life means how long it takes to decay to half its previous mass, half its previous amount. So for example, if there were 100 milligrams of something, 5 hours later, there'd be 50. And then 5 hours after that, there'd be 25, and then 5 hours after that, there'd be 12 and a half, and so on. All right. When they say the half-life is 5 hours, that just means every 5 hours the amount is cut in half. And the drug decays in the bloodstream, right? Reduces according to the differential equation, y prime equals ky, where y is the concentration of the drug in the bloodstream. What fraction of the initial dose remains in the bloodstream after 6 hours? Round your answer to 3 decimal places. All right, so I'm going to write this out. All right, the nice thing is they do give us an equation here. We'll start with that. And then plug in all the specific to my paper. So we're told that this drug behaves according to this equation. Now we've seen this already. Y has got to be equal to some constant times e to the kt. You saw me do this earlier, right? dy over y equals kdt. Integrate both sides, solve for y. You end up with something like this. Now, at 0 minutes, we're going to call that the initial time, the initial amount of the drug. We're going to call this y sub 0. The reason I'm doing that is because if you look at the way they're entering the answer here, they have y of 6 divided by, see this y sub 0? That's what fraction of the initial dose. So the y sub 0 here in the denominator, that's the initial amount, the initial dose. So that's why I'm calling this initial amount of the drug the initial dose y sub 0. Well, look at this. You have y sub 0 on the left equals c times e to the 0k on the right. That would just be c, right, because e to the 0 is 1. So the value of c is the initial dose. So y of t, y or y of t, right, equals, and then c is the initial dose, right, y sub 0, times e to the kt. And then one other piece of information they mentioned was the half-life is 5 hours. Right, so let's say, time has got to be in hours here. Then they even ask us about what fraction of the initial dose remains in the bloodstream after 6 hours, right? So time is in hours. So this means that the amount of drug in the bloodstream after 5 hours, right, when t is 5, is half the initial amount, half of y sub 0. And then after 10 hours, it would be a quarter of y sub 0. After 15 hours, it would be an eighth of y sub 0, right? Every 5 hours, it gets reduced by a factor of a half. But this is all we're going to need to find a value for k. So I put this stuff in, right? So when t is 5, y is half of the original dose. So I have half of y sub 0 on the left equals, c was y sub 0 times e to the 5k. Little t is 5 hours. Now you see, nice thing is, if I divide both sides by y sub 0, it's gone. Right? And now we just have 1/2 on the left equals e to the 5k. With the natural log of both sides, that's 5k equals the natural log of a half, and times 1/5, right? So k is 1/5 times the natural log of a half, which do things the way I've been doing them in the previous examples. I'm going to put this 5th in here, make this natural log of 1/2 to the 1/5 power. And I put this in for k in my model. All right, this is the model up here. I put this in for k. And very similar to earlier problems like with the Newton's law of cooling, we get the following. Y of t is equal to, y sub 0 times e to the kt. So the natural log of a half to the 1/5 power times t. And I can then do the same thing with t. When you multiply a log by some number, you can put that number inside with the power, and that becomes the natural log of a half to the t over 5, and then e to the natural log of something undoes each other. All right, so now we have this. Y of t equals y sub 0 times, and then, these e and natural log kind of inverse each other, and then you have just 1/2 to the t over 5 power. Now they're saying when time equals 6 hours, y of 6 is y sub 0, replacing t with 6 times in half to the 6/5 power. And what they want is what fraction of the original amount, right? They divide both sides by y sub 0 to get what fraction of the original amount is there left in the bloodstream after 6 hours. And so that's this number here. Y of 6 divided by y sub 0 is 1/2 to the 6/5 power. They're having us round this to 3 decimal places, right? So I'm going to enter this in a calculator. So 0.5, right? 1/2 raised to the 6/5 power. 6/5. So if a little about 43.5%, I'm going 0.45435. After 6 hours, because after 5 hours, there's 50% left. After 6 hours, there's, 43.5% of the original dose left. That's all this is saying. So 0.435 for the 3 decimal places. 0.435. Wonderful. And then run through the answer explanation. And it looks like that's complete. I believe I'm done. Yeah, 100%. Wait, so other than that little snag with the natural logs, so remember again, hopefully they fix it with my feedback. But for those of you watching now and haven't started the assignment, when you enter natural log or logarithms to raise the powers, you don't have to put parentheses around the log. Just write the log, and then after the log, put the power you're raising it to without parentheses. That looks like the way they want you to type them in. Again, a little annoying, but that's what I've discovered. Hopefully they fix that. Hopefully they find a way to have you be able to enter parentheses around the logs and then raise it to powers and still have it be equivalent like it should be. But yeah, and then so this should be it. This should be it for the assignment. Now, like I said at the top of the video, right? The problems I saw here may not be exactly the same questions that you see when you work on the assignment yourself, but the objectives are the same, and hopefully the problems are similar enough so that when you work on it on your own, um, watching me here will help you out in some way. All right, and thank you very much for watching.